Okay. So I thought a good way to start a graph theory lecture would be to discuss on the origin of this entire field, the origin of graph theory. Essentially, there was this place called Königsberg where there were lots of bridges. There were 7 bridges to be more exact, and like these are rivers. Okay, that's I'm slow at this, but basically there were like these rivers, and then there are these bridges, and there is land. Uh, okay, whatever. So the question was that can I start at, let's say, some place? Let's say I want to start here. I go across one of the bridges, reach here, go across this bridge, come here, something like that. And the idea is that I want to go through each of these bridges exactly once and come, okay, not even come back. Like, I just want to not repeat any bridge and cover each of these bridges on in like a single path. And the question was, is it possible? So this problem was unsolved for quite some time. Like, okay, not I can't really say that, but it was solved for the first time by Euler, who introduced graph theory to solve this problem. So first of all, any ideas which you people have on how this problem could be solved, or if you have seen this before, uh, just a interesting idea on how, like, where we can start. First of all, what do you think the answer is? Do you think it
No.
is possible or no? Okay, it's not possible. We have one answer. Anyone else? Anyone thinks it is possible? I think it's possible. Why not? Did everyone understand the problem? Because it's a bit vaguely framed. Okay, I'll take the silence as a yes. But okay, so like because this basically introduces the entire thing, I'll just brief up by uh, defining what graph theory and stuff really is. Essentially, graph theory, we have something called a graph, which is a collection of vertices and edges, which is called V and E. And it's something of this sort. So you have these points, which are like vertices, and then you join some pairs of these with edges, whichever ones you feel like, right? Something like this. I don't know. Some edges are joined, some vertices are joined, some are not joined. Your choice. It could even be empty, and it could even be a full graph where everything is joined. It's completely your choice. So um, the reason why this is so powerful is that despite it having like so few like it's a very simplistic nature, right? All I've said is like there are 5 points and I've joined some of them. That's literally what like 2-year-olds do, like connecting the dots and stuff. So I've really not defined anything too complicated, but yet graph theory is one of the most active fields of research in today's times, especially in like maths and computer science. And it's being used everywhere we go, like in stuff like AI, in stuff like data structures, in it's even used in like DNA tracing and stuff like that. Um, so graph theory is something which is very powerful despite a very, very simple nature. And okay, to start off, let's see how we can think about this problem we have on the left in terms of graph theory. So let's say I make this A as a dot, which is a vertex, B as another vertex, C as another vertex, and D as another 4 vertices. Okay. And I label them A, B, C, D. And each edge I join in between them is representative of like a bridge, right? So I have 2 ways to go from A to C. So I make 2 edges between A and C. So this is actually not a simple graph. Most of this class is going to be about simple graphs where you can have at most one edge between two things, but it's okay. Um, Similarly, between A and B, can anyone tell me how many edges there should be? Come on, people.
Two.
Okay, good. Between B and D,
One.
between A and D,
1 and
And
1.
between C and D?
1.
Okay. And between B and C, nothing, right? Unless we added some bridge here, which would completely change the problem. So let's not do that yet. So essentially the question has now become like, I basically want to start at, let's say, some D or somewhere, and then I want to go through this entire thing, covering each edge and never repeating an edge and never and like complete and go through every edge, right? That's what the problem has become. And this is actually something which is now called Eulerian path, Eulerian trail, actually.
Yeah, Eulerian.
Okay. And if you come back to the same place, it's actually called an Eulerian circuit. So there is a very simple yet powerful condition which is required for a certain graph to have an Eulerian path and Eulerian tail. Uh, I'm quite sure some of you might already know this, but uh, like, okay, what do you think that condition is? What is that condition? Anyone knows?
Can you repeat just what you asked?
What is the condition for an Eulerian trail to exist in a graph?
There needs to exist like at most two vertices with odd degree.
Correct. So that seems like very, very random condition, right? Why? What is odd degree? First of all, what is degree? What is going on? So the idea is that I can like kind of expand this ABCD. So I can think of it like this. So I'm just going straight and straight and straight. And like I go from A to C to B, maybe back to A and D and B, something like that. And essentially, I know that all of these, each of these, this edge, this edge, this edge, this edge, and this edge, they're all unique edges. What isn't unique is the vertices which will be coming because you'll have A again somewhere, stuff like that. But the thing is that if I take any vertex in between, something like the C, right? There is an edge before it, and then there is an edge after it. And that kind of uh, motivates this idea uh, that all of these edges are coming in pairs of two, right? So if I'm having an edge from C, I will also have another edge from C. The only time this will fail is at the first and the last vertex, because there'll be nothing after it and nothing before it. But anything in between, there'll be an edge after and an edge before. For D also, there's an edge after and an edge before. So I can basically say that if there is any edge, if there is any vertex which doesn't have degree. Now we have introduced this thing called degree. What is degree is it's basically how many edges is A an end point of. That's the degree of A. So for example, here degree of A is 1, 2, 3, 4, 5. So the degree of A is 5. Similarly, the degree of A is people
Degree of A you just said, right?
degree of B
Or 3. 3.
3. Yeah, degree of D,
3.
degree of C.
3.
Okay. So this is kind of the idea on why this like logically shouldn't exist an Eulerian trail, right? Because we realize that for anything except the first and last, the number of edges that it should be connected to should be like divisible by 2, right? Because you're getting them in pairs. So it seems kind of like wrong for there to for it to work out that you have odd degree at every vertex and you still have an Eulerian trail. So that's kind of the reason why the answer is no. The slightly harder part of the question is that if you do have only two places which have odd degree, oh, also it could also be like nothing as odd degree and you end at the same A, and then like, okay, this became odd here, but then that got neutralized over here at the end. So so the actual condition is either two places should have odd degree, two vertices, I'll say, should have degree odd or all even, right? One odd won't work. That's also an important condition. So the harder part of the question is actually proving that if there exists only two which are odd or nothing that is odd, there is an Eulerian train. Even that isn't like too hard. That's also pretty doable, but uh, maybe you people can take that as homework, right? That seems like a good problem to think about on why, if this condition is satisfied, then there should be an Eulerian trail. And in fact, if all are even, then there should be an Eulerian circuit. What is an Eulerian circuit? It's uh, just basically you'll have to come back to A. That's it. Like it has to be a closed loop. Eulerian trail will be like you start somewhere, end somewhere. Anyway, so till now we've been a little bit mixed up in our introduction and stuff like that. It's a little bit confusing. So let's just formally introduce what graph theory and graphs are. So we introduced vertices, edges, and let's say we have this graph, and we're basically saying that, let's say I label these 1, 2, 3, 4. Then vertices here are like 1, 2, 3, 4, and edges here are like 1, comma 3, 2, comma 4, 3, comma 4, right? And then we define this thing called degree. So stuff is getting a little bit complicated, but still understandable. That it is basically uh, number of edges, an endpoint of which is I. So this is the degree of I, like vertex I, whatever. So like 1 is the endpoint of only one edge. 4 is the endpoint of two edges. 3 is the endpoint of two edges. And 2 is the endpoint of one edge. Okay. So that's all we have defined till now. So one of the little bit sad parts of graph theory is that there are lots and lots of definitions. That's actually what scares a lot of people out of graph theory. That okay, you've defined a billion terms. Now, what are you even going to do with it? Like, I've just got bored. It's just theory, right? But sometimes it's important to learn that little bit of theory uh, because graph theory is something which can really like change a lot of stuff around you. I said this before, and graph theory is a very active field of research today, and it's being used everywhere in stuff like Google Maps to find the shortest path between two places. As I said before, in DNA, and in completely irrelevant and random things, you will never even expect some graph theory to be used. You'll just end up finding graph theory there. But okay, more on that. So we're talking about some points and we're talking about edges in between them, but what are like real life, um, you know, like applications of this? Like what can this one really mean? So we saw one example where this one was basically land and three was a bridge. So it's basically kind of like a map, right? That's one thing that's possible. That this is like land and bridges or something like that, and sea, something like that. Okay, or neighbors. You join two things if they are neighboring countries, something like that. Okay. Another completely different example is something like each of these is a person, and you join two people if they are friends, let's say, or if they know each other on Instagram. Then Instagram marks them with a label, so it knows that one knows three, three knows four, four knows two. So in some way, one is able to contact you. That's a kind of random example. Then it can also be used in something. Okay, just to give a completely random example, if you have, let's say, a grid
Most of grid problems are convertible into graph theory problems.
Yes, that's actually something which looks ridiculous because like okay, one might
But when
think
you
that
start to do it, it makes sense. Like if you try to approach the problem, it would make sense to motivate graph theoretic terms.
yeah, exactly. So, but like when I would talk about grid and graph theory, people would think like this is a vertex, this is a vertex, and these two are joined by an edge. But that's actually
Each cell
completely
is a
wrong.
vertex.
Each cell is a vertex is also not what I'm actually talking about. I'm actually
Oh,
talking
what?
about the more Hall's marriage kind of idea,
Oh, yeah.
where basically, let's say there are 5 rows and 5 columns. Then I put 5 points here. This is each of these are representatives of rows. So this is the first row, second row, third row, fourth row, fifth row. Then there are columns, right? And then let's say in this grid, I had for you, I liked some cells. So I decided to color them. I don't know why. I just felt like it. So I did it. And now this actually what this means here is that I can connect one and one if the corresponding grid cell is colored. And I could also color 2 comma 3. Okay, that's a bad line. 3 comma 2. Okay, this is a very symmetric graph, but 4 comma 4, 5 comma 5, and also 1 comma 5. No, is it 1 comma 5? Yeah, 1 comma 5. No, sorry, like that. Okay, so that looks kind of dumb, right? What is the point of that? And I won't give you
You
the
are
answer
like
of that right
trying
now.
to prove that in each row and each column there exists like one cell which is colored.
Yeah,
That
there
means
are a lot of those kind of problems where sometimes you want to, like those queen kind of problems, right? Where you want some queens which don't attack each other on the chessboard.
yes.
And
Then you can like define the edge to be from one cell to the another where the queen slash any chess player can move.
yeah, those kind of things are like very useful in graph theory. And we'll
Yes.
actually do one problem later on where you have to do this conversion, which I've just shown right now. But for now, let's go back to the introduction of our few things in graph theory. Or okay, I'll just do it below. So we spoke about degree. A connected term is something called neighboring vertices. So essentially, if you have this graph, um, 1 second. Okay. And oh no, what happened? Okay. 1, 2, 3, 4, 5. And I have some edges. Then I can say that 1 and 3 are neighboring vertices if they're because they're joined by an edge, right? So I can say 1 comma 3 are neighboring. I can also say 1 comma 5 are neighboring. I can say 5 comma 3 are neighboring. I can say 2 comma 4 is neighboring. I think that's it. But I can't, for example, say 1 comma 4 is neighboring, right? I cannot say this because there is no edge between 1 and 4. If I made an edge, it will become like that kids connecting the dots question again. Uh, but okay, so we talk. So neighboring vertices is okay, but like sure one like okay, I should probably make a better example for that. Yeah. So like now I by the way can't say 1 and 3 are neighboring vertices, but I can still say there is some way to go from 1 and end up at 3, right? So 1
That
and
is a
3 are
path.
connected.
Yes.
Yeah, there is a path. Exactly. There is a path from 1 to 3. But they're not neighbors. You can't directly go from 1 to 1, but there is some way, right? You can end up at 3 after starting at 1. So that's good. Um, so what we are defining, we have defined 2 more terms. We've defined a path, and we've defined if 2 points are connected. What do each of these mean? path means that path is basically like just a collection of vertices, each two of which are neighboring. So it's something like 1, 5, 2. Or okay, if I join this one for you, then it could be something like 1, 5, 2. Oh wait, not 1, 5, 2. Sorry, 1, 5, 3. 1, 5, 3, 2, 4. This is a path, right? Because I'm going from 1, 5 to 3 to 4. That's a path. 2 points are connected if and only if there is a path in between them that joins them. Okay, this is enough, right? We've got so much theory already. I'm not interested in doing more. I'm bored of this. Let's get into I think one of the most common problems that you'll like hardly ever see anyone teach you graph theory without doing this problem. It's called the handshake lemma. And what this problem basically asks you to prove is that let's say there are n people at a party. Maybe they could be mourning their death or someone's death also. They don't have to be up at a party, but eh, let's just be happy. Okay, n people at a party, and some pairs of them choose to shake hands. Okay, now we don't know how many of them chose to shake hands with how many people. We just know like one might have shook hands with 4, 7, 8, if I'm labeling the people. But like we really have no idea. And after the party, we went to each person and we asked them, how many people did you shake hands with? Okay. So let's say one replied with, okay, I shook hands with like 3 people, two shook hands with like 4 people, and so on. And then you sum up all of these. So 3, 4, let's say the final guy shook hands with 8 people. And you sum up all of these and you get a number. The question which they're asking you to prove is prove that this final number is even. Just to repeat the question, there are n people at a party. Some pairs of them choose to shake hands. And at the end of the party, you go to each person and ask them, how many people did you shake hands with? Each person answers truthfully, hopefully. And after
What
each
if
of
a
them
person
answer,
doesn't has hands and he's shaking hands with legs?
in that case, they weren't invited to the party. You can just we did not. We're a bit, discriminatory. Uh, Okay, but so you add up all of these numbers, which all of the n people gave you, and you get the final number, and prove that that final number is even. That almost seems like a magic trick, right? Boom! I just added some random numbers, and I'm already guaranteeing that it's even. I don't even know what the numbers are. I have no idea. So I think some of you might have seen this problem before. Someone other than Anurag, please come on, speak up. Anyone knows how to solve this problem? Even if it's through chat, it's okay. Come on, people. Just ideas, even if you don't know what like the exact what whether your idea will be correct or not. It's never a bad idea to give in an idea. By the way, what am I sharing? Am I sharing my full screen or am I sharing only this tab?
You are sharing only this.
Okay, so what do you see when I do, say, this?
Nothing.
Nothing. Okay. It's
I
interesting.
can just see the screen only.
Okay, okay.
That handshake lemma thing.
Fine, fine. Come on, come on, come on. Do you want me to go around and asking to unmute? Yep, kinda. Okay. Ishan has messaged me. I've already seen this problem. The basic idea is each handshake is counted twice. And Kanav also wrote the same thing. So that's exactly the idea. First of all, just to get this into graph theoretic terms, we can think of this as n vertices, and you join some pairs of them with edges if they shook hands, right? Uh, and otherwise you don't join by an edge. Some people didn't want to shake hands, so you don't join them by an edge. And the basic idea which I got from both the people is that uh, what I'm basically counting at the end is the degree of each vertex. Like if one told me that it shook hands with two people, that means that the degree of one was two. So at the end of the day, I'm basically doing sigma of di, where I is going from 1 to n. And my question is to prove that this is even. So, as the idea was, it's basically the thing is that um, any edge. So rather than looking at this from every vertex, where I'm thinking of it from vertex 1, then vertex 2, vertex 3, vertex 4, vertex 5, and on, I will think of it edge by edge, right? So this edge between 1 and 2, when does this get counted? This gets counted when I am counting when I'm counting the degree of 1, and it gets counted when I'm counting the degree of 2. So any edge gets counted twice. So I can actually write this as sigma 2, and you're going from I equal 1 to number of edges. Okay, that's a bit weird, but essentially what I'm trying to say is that the total sum is going to be 2 times the total number of edges, because any edge gets counted twice at the end of the day. And this is actually a very, very common trick in graph theory, which is the idea is of double counting, if you've heard of it. Uh, Double counting essentially says that you can, you know, instead of thinking of this vertex by
Count
vertex,
things into it and just equate.
yes, exactly. Count things rather than counting it vertex by vertex, I can also count it edge by edge and then equate them. Okay. So I have been going a bit slow and been giving more of an introduction type thing. By the way, is this hang? No, is this hang? Oh no. Okay, wait, I'll restart sharing. Should work then. Hmm, Give me a minute. Okay, I think it's working now. Yep. So now let's get into a few more interesting terms. Let's start by introducing a tree. Or, okay, before we introduce a tree, let's introduce what is known as a cycle. So essentially what a cycle is that it's like a path where you're starting somewhere, going through some edges and ending up somewhere, except at the end you will have to come back to the starting place. So it's like a polygon, I guess, but it doesn't have to be like a polygon, because for instance, I could also have a cycle um, like this. And that's an important idea in graph theory. It literally does not matter what the geometrical shape of the thing is. Like these two cross over here, that doesn't mean I've made a new vertex here. It just, it's irrelevant to me. This same thing is equivalent to this thing. Because if I label these as 1, 2, 3, 4, 5, and I label these as 1, 3, 2, 4, 5, it works. let's say 1, 2, yeah. These two are literally the same because I've connected the same pairs of edges and I have the same vertices. So whether I reshaped the thing is completely irrelevant. So, okay, but coming back to cycles, also, by the way, these graphs are called isomorphic. That's another interesting thing if you want to read about. But cycles are essentially where you start at a certain vertex and go across some edges and you come back. That's a cycle. Now, the problem with cycles is that, okay, they're often very, very useful. And we'll do a few problems maybe where we see how useful they become. But sometimes they become problems. Like I've taken a class on something called dynamic programming, if you people have heard of it. I'll just give an example from that. Dynamic programming is nothing but recursion. So essentially, the thing is that, let's say I am trying to say that solving one is equivalent to solving two. Solving two is equivalent to solving three, like induction. Three is equivalent to four. And then I just know how to solve four, which is like a base case. And so it's done. So the problem is that what if this graph had a cycle? What if 4 was connected to 1? So I'm saying 4 is equivalent to solving 1, but then I don't know how to solve 1. So like, let's say my base case was some 5, but I'm saying 1 is equivalent to 2, 2 is 3, 3 is 4, 4 is 1, but I don't know how to solve any of them. So that's the problem with the cycle, that often this could even cause like an infinite loop of your computer program, because maybe you're asking it key, you go to the next equivalent one and it'll keep trying to go to the next equivalent one, but it'll come back to one. And it'll go to 2, 3, 4, 1, 2, 3, 4, 1, and then just stay stuck there forever. So that's why we sometimes don't want these cycles to exist. However, we do want one thing, which is connectedness. So we do not want cycles, but we want connectedness. What does connectedness mean? It just means that there's a path between every two vertices. Like there isn't any, like if you have something like this and you have these two, this is not very good because I can't get from here to here, right? Whatever path I take, I will be stuck inside this component and I will never be able to reach this component. So I do not want um, something like this where it's disconnected. At the same time, I don't want there to be a cycle. This introduces the most important, in my opinion, concept in graph theory, which is a tree. A tree is basically a minimally connected graph, which means that it doesn't have a cycle, but it is connected. So essentially, the good parts of cycles are that, okay, I've spoke so long about why they're bad, and now I'm suddenly saying they're good. So they're all just concepts. It's not good or bad. So the interesting thing about cycles are, even if I delete this 5 and 4 ke beech mein edge, 5 and 4 are still connected because I can go from 5, 3, 1 to 4, right? But in a tree, if I try to do that, like for example, this is a tree because there is no cycle and it's connected. So in a tree, if I try to delete this vertex, sorry, delete this edge. 1 second. Oh, I shouldn't delete the vertex itself, right? So this edge, if I delete it, now it's become disconnected, which is not good. In fact, if I deleted this, then also it's disconnected. I deleted this, then also it's disconnected. I delete any edge in a tree, and my graph will no longer stay connected. That's kind of a, now you will say this is a problem with trees. You don't like this, but you often like this a lot. That it's a very strong structure where it's so powerfully bound that you can create a lot of conditions. For instance, um, in a general graph, there can be only one edge. There can be no edges. There can be n into n minus 1 by 2 edges, which is n choose 2. But in a tree, there will always be n minus 1 edges. Can anyone prove why? Oh, I received some chat messages.
What is n? Hello. What is n?
What is n? N is number of vertices.
You can just induct on the number of branches and stuff.
Correct. So one of the most powerful things about trees is induction, and it works unusually well. Like we spoke earlier about double counting, and that worked a lot very well because we could convert vertices sigmas to edges sigmas, and something which works very well with trees is induction. And the basic idea is, as you said, okay, first of all, let's just draw a few trees for our understanding. One second. Yeah. And this is a tree because there is no cycle, and it kind of looks like a tree, right? It's like those branches of a tree. So that's kind of where the name comes from. So as Anurag said, I will kind of try to induct. And there's not just one way to induct, there are multiple ways to induct over here. Um, One simple way is to, let's say, select a random edge. Okay.
We
I
can double
select the
count it too. Uh,
double
like in
count.
this, yes.
Okay. How
Like
will you
say
do
there
that?
are k in some stage, m in some stage, so that it becomes 2 plus 2m and so on.
Sorry.
And like say degree of some number of branches, some is the uppermost is k, then the downmost is j, and just say it keeps counting, and in the end it becomes like each thing's double, and it's just like you just 2 upon 2 and you get n minus 1.
Huh? Okay. I kind of get what you're trying to say, but like just to make induction is just a more formal way of saying
Yes,
that.
because it's really non-rigorous to double count,
Yeah.
because in I just introduced some non-rigorous thing.
Yeah. It makes like sense, but at the same time you want to be more mathematically precise, I guess. That's the thing. But anyway, so basically what I'm going to do is I'm going to choose a random edge. I just like that edge and I'll delete it. Big deal. It's gone. So what's happened now is now I have two smaller trees. This is a tree and this is a tree. Why is it a tree? If you're confused about that, figure out yourself. I'm not going to answer that. But the thing is that because of induction, let's say like our inductive hypothesis is that um, like for some n edges, we'll use strong induction. Sorry, n vertices, or let's say k vertices. There'll be k minus 1 edges for all. I'm hoping people are like familiar with basic induction. And basically, what I'm trying to say is that if it's kind of like the domino thing, right? Where you're assuming that something is true for all the smaller cases, and then building on that to prove that your current case is also true. So essentially, like this was a graph on what 1, 2, 3, 4, 5, 6, 7, 8 vertices. But I have now split it into two trees. One has 3 vertices and the other has 5 vertices. And for each of those, I already know that the answers of the tree is going to be 2 and 4 by my inductive hypothesis. And so I'm going to do 2 plus 4, and then this one edge that I deleted, that's 1. So 2 plus 4 plus 1, which should come back to 8 minus 1. So, okay, more formally, when I do that, I'm splitting into two trees. One will have k vertices, other will have n minus k vertices. This will have k minus 1 edges, this will have n minus k minus 1 edges. and then there'll be that extra one edge. And if I add all of this up, I'll get n minus 1, right? So this is kind of there actually, okay, anyone has another inductive proof for this, where you do not delete an edge? Come on, people.
You remove vertex.
Remove a vertex, perfect. Let's say okay, I'll just redraw it. 1, 2, 3, 4, 5, 6, 7. Okay. Now let's say I delete vertex, let's say 5. I don't like 5. Okay. So I delete 5. I also delete all of these edges. And hmm, okay, maybe 5 is not a good idea to delete. Just delete 1 for the sake of the example. It works wherever I do it, but I don't want to make like empty graphs. But okay. So let's say I delete 1, and along with it, I'm deleting these 2 edges. So what's happening is that now I have, let's say, degree of 1, which is the number of edges from 1, is k. And essentially, I am creating k trees, which will be each of these k things. Here it's 2 trees. It will be more. Okay, and for each of those k trees, I know the answer. Then I can add all of those up and then add k. And I mean, like, I'm not gonna do the calculation. You can figure out yourself that you'll come back to the same n minus 1.
Okay.
So, yeah, anyone saying something? Hello? Okay.
Yes.
Anyway, let's see, which problem should we do? See this one? Oh, I added Atul. Um, yeah, this is a nice problem. So I'll just give a brief introduction to the problem. There is a graph G which is connected. It's on n vertices. Atul wants to delete some edges so that at the end of the process, each vertex is an endpoint of an odd number of edges. Under what conditions of n on n can Atul complete his wish? So I'll give you all about 3 minutes, after which we'll talk. Okay, 1 minute only, but still. Any ideas? Any dumb thoughts, anything that you just want to put on the table, any claimed answers, any fake solves, anything?
N has to be even by handshake.
Yep, that's the first idea. That by Handshake Lemma, which we discussed earlier, is that here. Basically, what is happening at the end is that this each vertex is an endpoint of an odd number of edges. Basically means degree of each vertex at the end should be odd. And if you had only an odd number of vertices, then you're basically adding odd number of odd numbers, which basically odd into odd, not odd into odd exactly, but like adding something like 5 plus 3 plus 5, three odd numbers, and that's destined to give you an odd number. Except you know that it's 2 times e, which is even. So that's not good at all. So we're already saying that by handshake lemma, we have that n cannot be odd. The real question now is, does n even work? Guesses? Do you think it works? Just by examples. Maybe sometimes for some graphs on even vertices it works. Maybe some graphs it doesn't work.
Only for some it does.
Uh-huh. So
It doesn't
let's
work
take this.
for a tree.
Doesn't work for a tree. Give me
For
an example.
some trees,
Okay, give me an example. Some tree.
Like take the top root and take phone
Just how
for
many vertices?
4.
Okay, 1, 2, 3, 4. Now what to do?
Okay. No. This 4 is like
Okay,
a
okay.
node
It's
with
fine.
2
I'll
and 3.
join whatever you say. Just tell me.
Okay. 1, 2, 1, 4, 1, 3.
1, 2, 1, 4, 1, 3. Okay.
You delete
So
any of the vertex, you get that at least one has like even number of
see, but I
even
don't
degree.
need to delete anything, right? This itself will solve the problem because
Okay.
once you delete some, it can be no edges also. Like, come on. So at the start itself, this guy has degree 1, this guy has degree 1, this guy has degree 1, and this guy has degree 3. So problem is solved. Next example. That didn't work out. Maybe something else will work out though. Who knows? Any other possible counterexamples? Okay, how about this? Let's take a random example on 6 vertices. 1, 2, 3, 4, 5, 6. And just for fun, I'm going to make it a tree again. And now try to tell me how to make this work. What should I select? What should I delete rather? Or okay, just tell me what I should select. That's easier.
Delete 1 comma 5.
Okay. Um, let's use red, I guess. 1 comma 5 gone.
Then you're done.
We're done. Oh wow, we're done. That's good. Maybe I'm going to make your life a little harder because I'm just um not happy. So
Like
what
this,
should I
add
do?
another what is like 7, which is connected to 5. No,
Okay, sure.
yes. Now you
Oh
can't,
no,
I guess.
now I can't. Okay,
Yes,
interesting.
So now the number of vertices is odd.
yes,
Oh yeah, now the number of vertices are good point.
yes.
So let's do that.
And
No, now I can just
no,
delete this one. Okay.
yes. But
So
still
that's a
5. Yes. So
let's what about something like this? 1, 7, 8. So like after deleting 1 comma 5. Now 1 is joined to an even number of things.
Delete 1 7.
Yeah, delete 1 7. Okay.
I guess just prove
So
it for any connected graph with n vertices.
okay, now this is an interesting point where we've reached, where we've been trying stuff with trees, and we're now thinking about connected graphs instead of just trees. Now, the question is, if I can prove this for trees, if I can prove this result for trees, am I done? Because like
I
instead
guess
of G being,
like any connected graph is a tree with some one more edge added to it.
okay, that's a strong claim. Why do you think so? Yeah, it's true, by the way. I'm not trying to scare you or anything. So Shan was going to say something.
We define tree as a minimally connected graph, right?
Sorry?
At the beginning of when we started discussing about trees, we defined
Hmm.
tree as a minimally connected graph, right?
Yep. Yep.
Yeah, so by the definition, we are done, right?
What are we done by?
Like
Like
Okay.
a
any
tree
other
is the
connected
minimum.
graph is a tree in some way. You can just remove some edges in it and you get a tree.
Exactly. So a more formal way of putting that is there is this notation of something called a spanning tree. A spanning tree is basically a subgraph where you have deleted some edges, the way Atul is trying to delete some edges, and you have ended up with a tree. So why can we create a spanning tree is the question. And you're all right that it's a minimally connected graph. Any other thing has extra things. You delete those and then you will get a tree. But a more formal way of putting it is, let's say there are some cycles in this graph right now. And we know that if we delete some edge of a cycle, the graph is still connected. Because if I delete, okay, let me label them 1, 2, 3, 4, 5, 6, 7. So 1, 2, 5, 3 is a cycle here 1, 2, 5, 3, 1. And if I delete something like 5, comma 3, um, the graph is still correct. And now I have another cycle 2, 4, 5. I delete this one, for example. Or I could delete any of them, literally anything from the cycle. And the graph is still connected, but the number of edges is reducing. So at some point, we will have only n minus 1 edges left. Then it'll be a tree. That's it. So that's kind of why every graph will have a spanning tree. And like basically the idea on why you want to change a graph into a tree, it feels like graph is a much more stronger condition than a tree. So why would you switch to something which is seeming to be harder? It's because if you can't prove it for a tree, then you can't prove it. Like if you can't prove it for a tree, then you don't know what the answer is. And if you can prove it for a tree, you can prove it for everything. So it's better to like just start with a tree and hope that you can prove it for it. So we almost saw the answer there in those examples, except it was more of intuition than, you know, exact this thing. Okay, one very interesting thing about a tree, which I do not know why I have not discussed it now, is something called a leaf.
We can just like delete some edge with a edge from vertex that is an even degree, and just we will just like get some another tree. We can just then induct on the number of trees easily.
Mm, wait, everything has odd degree here? No, one has even degree.
No, like I'm saying,
So
something
you're
has
saying like,
even
okay, let's say
degree.
one here has even degree. So I'll delete something
Just
from
delete
one.
1 5. You have like 2 trees. Yeah.
Hmm.
So induction seems a good thing.
But 5, 6,
Okay,
7
no,
is
I'll
3
give you a
vertices.
problem. I'll give you a problem. Let's say 1, 2, 3, 4, right? So when you're being a little too careless, because when I said that like one has even degree, so I want to delete one of one's neighbors, and I end up deleting this guy. Now two will have even degree, and you can never make it have odd degree. because it's not connected to
You
anything
can
else.
just delete 1, 3.
Yeah, exactly. You want to delete 1, 3, but why? Why not
3,
1,
4
2?
is a tree in some way.
Okay, but that's still like because because you know the current scenario, right? You can't say in a proof that I will delete the one which has a tree below. What if both have a tree below, but somehow it doesn't end up working in some way? For example, something like that. Now, if I delete 1, 2 here also, um, now 2 is connected to an even one. And if I delete 2, 5, then 5 is connected to an even one. And then I'm stuck. So the only ways I should have
Delete
deleted
1, 3.
3 in the first place.
Yes, you get 2 trees in any way.
Hmm? Yeah, you'll get 2 trees anyway. You can't create 1 tree. That doesn't work. But okay, just coming back to what we were talking about, which is the leaf. By the way, till what time is this class? 10:45, right?
Yes, 10:45 or
Okay.
10:30, it is your wish.
Okay. So I've been going a bit slow. I was hoping to do a few more problems, but it's fine. We have one more class tomorrow.
You are defining leaf.
Yeah, exactly. So a leaf is basically a vertex in a tree which has degree 1. Now the main question about a leaf is why? Why should a leaf exist?
Like just take the endpoints. It is a leaf.
Endpoint of what?
Endpoint of the tree.
How
Like
do
the
you
node,
how
node
do you
leaf,
define
what
the
we say.
starting point of a tree? I've just put one over here, but I could
One is
always
like
think,
the root. One is like the root. And this tree has
yeah,
to end
I've
somewhere.
rooted it, but it doesn't make it the root. I could have thought of 3 as the root. And then I have something like 3, 1, 4. 1 say you're going to 2, 2 say you're going to
But
5,
it
6.
will end at some point. It will not like grow more branches out of anything.
Yeah, but like why?
Like because if it doesn't, then it has greater than n-1 edges. And which is a
Why?
contradiction. You can double count.
Exactly. That's what I was looking for. So if everything has di is greater
Like
equal
just
to
delete the upper vertices and get the end ones. And you will just
the upper vertices.
like delete the upper one branch roots. You just delete it. You don't need it anyways. And you can
Why would
just
I?
induct them.
Okay, I'm
Induct them.
deleting 1. Now what?
Yes.
Okay, now
Now
I'm
you can
deleting
just
3.
induct. You can just
And
induct.
now I've reached 4. That's what you're saying. Okay, sure, that also works, but it's a little bit I like this other double counting proof more. I mean, even this is fine. Like you basically route it randomly where you decide some vertex as a starting point. And if it has degree 1, great, you're done. If it doesn't have degree 1, you delete it along with all of its neighbors. Like not its neighbors, but all of its edges. Now you have like some trees. Now it's kind of like induction. Um, but okay, the other proof is something like this. So we know that sigma di is what? 2 times the number of edges. And for a graph, this is equal to exactly 2 into n-1. But this guy we are saying is at least 2 into n because each di is greater or equal to. And that doesn't work for us, so we are done. So what did we get? We got each tree has a leaf. Leaf is a vertex with degree 1. These are often very, very useful for induction. So for example, for the proof of trees itself, if instead of deleting random edges and random vertices, if we had deleted a deleted a leaf, that would make our job really, really easy because now it's almost the same structure except one vertex is gone, one edge is gone. So instead of proving n-1, you're proving n-1, n-2. And that's done by simple induction. You don't even need
I guess this
strong
leaf
induction or
definition
anything.
can help you prove the tree partition thing.
Partition.
Like partitioning the graph into trees.
Okay.
The connected,
Uh,
I guess. Like trees into trees. So say like some vertex has even degree. Okay.
okay.
So if that
Wait,
one vertex has
I'll make the graph.
okay. make it.
Also, one random thing, but it is super useful to draw random graphs for graph theory problems, because often half the problem is in just, trying out random stuff and seeing how you want to figure out stuff and seeing patterns, creating conjectures and stuff like that. Yeah, go on. Anurag. Hello. Okay, meanwhile, we now know that this graph has a few leaves. So 4 is a leaf, 5 is a leaf, 6 is a leaf. So these leaves are actually what are the most useful to us when we come to inducting. And okay, just to remind all of you of the problem, it's been like so much time since we were talking about the problem. The problem was that we wanted to delete some of the edges so that at the end of the calculation, each of the di's is odd. And the idea is that we know that each of the leaves has degree 1. So all of its moves are forced, because if I delete this thing between 4 and 2, then I can never be done, right? Because 4 has to be connected to 2. That's the only way, because it needs to have odd degree and it has degree only 1. So it can have 0 or 1 based on whether you delete that edge. So this move is literally forced. So I cannot delete this one. Same way I cannot delete this one. I cannot delete this one. My only options in life are deleting this one and deleting this one. So that's where the problem starts. So let's say I try to induct, and the thing is, if I try to delete this 2 and 5 and think of this new graph, now it suddenly has odd number of edges. So it shouldn't work by logic. So we've certainly done something wrong, because we can't like just delete it and forget about it. What instead we should try to do is, instead of thinking about just one leaf, we think about its parent and we think about the other leaves from that parent.
Like you can think the parent as a leaf. If that parent has some even degree, just delete the upper vertex to it, and you get like some another tree.
And yeah, so it's like if parent is okay, let's say all of these are leaves, right? There are 5 leaves starting from a common parent. Parent is basically whatever you can think. Parent is the one above. Um, so essentially, I am joining all of these, and there are 5 leaves over here from this parent. So there are 2 cases. Either there'll be even number of leaves or there'll be odd number of leaves. Each of them you'll have to do a slightly different thing. So what happens is, see, first of all, let's say 6 are there, so even are there. First of all of these will have to stay. That is for sure, right? Now, we also know that we need to keep after the induction step, we want to keep everything still to be even. So my basically 2 options was, after deleting everything the induction, I can either get rid of everything or I can get rid of only these leaves and I can keep this parent with me. So the basic idea is, if this thing is even, if the even number of leaves, then I'll delete only these leaves and I'll keep the parent with me. And now I'm kind of inducting on this other tree, which also has even number of edges, because even number of vertices, because I've deleted an even number of vertices. And if there were an odd number of leaves, something like this, now I will delete this guy also along with me. Does that make sense? Because uh okay, while deleting this guy, I will also delete this edge and possibly some other edges. So, but at the end of the day, now I have 6, I have lost an even number of edges, and I've also made sure that each of these has odd degree, because this guy has odd degree 1, 2, 3, 4, 5, and each of these have degree 1. And now I'm inducting on some other trees. There are some other trees which this was connected to. So that's really the power of induction, that I could get rid of one part of this graph, and I can say that the other parts it's doable. So this part also it's doable. Fine. Solved. So that's kind of the power of these three kind of problems. I'd like to uh now go on to something which is okay, this is also a good problem. Let's do this. Wait, did I do this? No, this is a different problem. Okay. Okay, think about this for, let's say, 2 minutes. This is not a very hard problem. Yet it's a very nice problem, that's for sure. I like this problem a lot. Also because I could actually get it. Oh, I should probably just give a intro to the problem. Basically, you're starting with a graph which is not a tree, it has a cycle in it. Um, and we don't know whether it's connected. That's also kind of sad. But for the sake of the timing, let's say it's connected. We'll see why that really doesn't matter at the end of the day. But let's say this was some cycle, and in any step, we are choosing the cycle, and we are making a new vertex. Let's say that's with blue, and I make it here, and I connect it to each of these, and then I delete these three edges. So I convert the graph into this. And okay, here we got lucky that there is no there's no cycle left. But okay, maybe there were some other cycles, and while getting rid of these cycles, we got a few new cycles with blue edges. And the question is that even if this thing happens, because you were adding new stuff, you ended up creating new cycles. At the end of the day, after some number of steps, you will have to stop. There will be no cycle left. Why is that?
This
That's
is
the question.
intuitive. Okay. Can I just
Sorry?
tell the answer? Can I just tell the
Yeah,
answer?
sure. Sure. Go ahead.
Like take some graph G which has k cycles.
Okay.
So in a move,
Cycles.
yes, any k cycles. So in a move, we choose any one cycle, complete
This
cycle.
one.
Yes,
Mhm.
okay. Okay. So, and you just like make it something like and in the operation that is given.
Okay. So I'll make these three.
Yeah.
And
And the
I'll
connected and the another if another cycle is connected to it, we also do the
okay,
same
wait,
with them
wait,
and
wait.
get something like one complete cycle.
1 second.
Yes.
See, I
Okay.
just want to make one thing clear. No, I
Okay.
should okay. This was what the graph was before,
Yes.
and now I have deleted some stuff. So now the graph is more like
Yes.
this, right?
Okay. Okay.
The
Now
problem
bottom
is
delete.
edge,
now there is a new cycle
the bottom edge
which
shouldn't be there,
wasn't
right?
there earlier, and there's a new cycle here
Now
also.
select the
So
old cycle which was there and just delete it.
old
The, bo-
cycle.
the
There's
bottom
no
edge
more
shouldn't.
old cycles.
Oh, wait,
Everything is
isn't
in.
the whole square a cycle itself? I'm talking about
Yeah,
distinct
sure, but
cycles.
I'm not. I can choose. Okay, yeah, there are three cycles in fact here. You're right, but I don't. I need to choose the full cycle. I can choose any cycle I want.
So you are telling like I do it in any way it will
Yeah,
work.
Yeah, so
I
Yes,
will
it
do
will.
it
It
in
will.
whatever way I want, but you need to tell
It
me
will. It will.
ki it
Yes.
will end even then. Yeah.
Yes. Yes. Okay.
Also,
yeah, just one thing. Won't the bottom line also go off in this one?
Uh,
Bottom red line,
sorry.
it's also
Wait,
the
this was the
bottom red line is
original
also
thing.
an NT, right? Yeah. So in the
Uh,
diagram left, won't the bottom line also go off?
1 second. What? Oh, okay. Yeah, you're right. My bad.
Yeah, so I think we can
Uh,
prove that like whenever you perform an operation like this, number of cycles reduces by at least one. Even if you consider a new cycle occurring with two blue vertices, that's only possible if there was initially a second path connecting the vertices A and B, which are now connected by the blue vertices. So that second path connecting A and B, due to the initial direct line between A and B, would in itself had created a cycle beforehand. So that would have been that cycle even before this new cycle is created.
Okay. What do you have to say about something like this? And now I choose this cycle
Yeah.
and let's say I make this, I join each of these.
Yeah. So only if, so there'll
Okay,
be when you,
1 minute. Sorry, I'll make a few more irritating things. Uh, so the problem is now this is a cycle, this is a cycle, this is a cycle. There are way too many cycles, I can't even count. And even the starting had a lot of cycles, I agree. But
yeah.
can we really claim that this number of cycles is reducing?
Like taking monovariant makes
Yeah,
sense,
because
but here
see,
it will not.
when you remove an edge, it won't actually have, it see when you remove these edges and you just consider two of these points to be A and B.
1 second, maybe, yeah, you're right. I should label these things.
Yeah, let the
1,
new
2,
vertex added be
okay,
C
you tell
by
me how many vertices do you want in the graph?
any numbers. So since we were going with
No,
4
just give
plus
a good example with random
and
edges
5.
and
Just see, Rushil, it will end at a tree. It is a big thing.
okay, we'll keep that for some time. Let's first figure out what is going on here. Um, okay, you said that when we okay, choose a cycle. Okay, I'll choose the cycle. Why would you choose the cycle? Let's say I choose 154. Okay, and now
Yeah.
I join these three, and I get rid of these three. Now we're claiming that the number of cycles is reduced, which might be true actually. I'm not sure. Why do you think it's
Yeah,
reduced?
so what I'm claiming is, okay, there might be new cycles created. So in this case, it will be O134 is a new cycle. However, a
So
new cycle, okay,
X431, yeah,
X1
you're right.
to, yeah, X431. However,
And
such a new cycle
X541
can only be created if there is a path between 1 and 4 different from the initial direct edge joining 1 and 4.
correct.
Which means that there was already a cycle existing between involving 1 and 4 and the other paths in x1, 3, 4 and other points in x1, 3, 4, other vertices.
Yeah, that makes sense. Um,
So the same can be said for any new circle you add is essentially basically just adding the vertex x to a pre-existing circle and removing a direct, like removing
okay, but why
this
has
one.
the number of cycles reduced?
Yeah, because cycle 154 has gone.
Okay, okay,
Can I
that
also
does
take
seem
like,
to
but
What
new
if it-
cycle X431X has come.
new cycle 4.
431X.
Yeah, so he's basically saying that 431x5 only managed to come because 4315 was already a cycle, if I'm not mistaken.
What about X43125X, something like that?
X432.
X431, and then if there's an edge between 1 and 2, or like X14, or
Okay.
like X43125X,
X1342.
ones which go over multiple edges in the cycle.
So
The number of cycles did not reduce it, just like became the same thing. You deleted one cycle and you formed another in some way. And
no,
But
but
the
he's
original
saying the
cycle is
154 cycle is gone.
145 cycle has gone, but X431X cycle has came now. Let's see.
Yeah, but the X431 cycle is essentially a 143, the cycle 143.
So he's
Okay.
basically saying if X came
Yes,
between
he's
1 and
correct.
4,
Yes,
then
yes.
you can, it's like a bijection kind of.
Yes,
So
yes.
you're saying any cycle which is like 1x342 or something. So 1342 was a cycle earlier.
Now he's saying like 2 delete 1, 3.
And 1342 is not a cycle
Yes.
anymore because 1 and 3 are not connected.
But if you delete this cycle, oh wait, if you delete this cycle, this reduce. Like for say you delete the 143 cycle. Okay.
Say okay, 145
Okay.
cycle I deleted.
Okay, now you deleted 143 cycle.
On the next step, fine.
Hmm.
Just do it with 14. Okay, fine, I'll do
Okay.
it.
You need to do it.
Okay.
Like just do it for 1-4.
Bye.
1-4 also makes sense.
1-4. How will you delete a 2 edge thing? That's not even a cycle.
It's a cycle. 1 and 4. Go to 1 and 4. No.
Okay.
Delete 1 for
That's not
3.
a cycle. Come
Yes,
on.
yes. Delete 1 for 3.
Delete 143. Fine. I'm not erasing because then stuff flies away.
Okay.
Oh, by the
Okay.
way, 143 is not a cycle.
Why you
Like we
just go to
deleted 1
1,
4.
4, 3,
We
1.
deleted 1 4. Should I get rid of this
Oh
X
yes.
thing?
Yes.
Fine. This is going to. Oh wow.
I guess this number monovariant thing is causing some troubles.
I have another idea.
Go on.
When we delete the edges of a cycle, then we are reducing the degree of every vertex by 2. And then
Right.
then after we add the vertex and join it with all the vertices, then we are increasing it by 1. So basically
There is some another guy named me and he's speaking right now.
we are effectively reducing the degree of every vertex in that cycle by 1.
Wait, okay, I just noticed 2 Anurags. Are you people the same or what? But okay,
You
you've
recognize my
mentioned that,
voice, Rushil. You do
yeah,
recognize my voice.
but I don't know, I got confused.
Just
But
rename
okay,
that
see,
guy
the
to
problem with
XYZ.
what you're saying, Anurag Singh, is that you're right, we reduce the degrees of the people in the cycle, but now we have one more person. So in fact, like at the start, we let's say had a cycle of length 4. So we deleted 4 edges, but we have added 4 new edges. So the number of edges is literally the same.
Yeah, but degree of every vertex is reduced by 1.
But we have a new one which has degree 4.
E by V strictly decreases.
Yep. And that's also what Anurag was saying earlier, that we'll end up with a tree. That's actually okay. By the way, I really like this cool proof that this is kind of like a bijection where I'll still have to be double sure on whether this works, but I'm pretty sure it does. That essentially that if 1x342 is a cycle now, that means 1342 was a cycle earlier. And 1342 cannot be a cycle anymore because 13 edge is gone. Okay, but coming to the neater proof, I think, although even okay, I'll not say neater or not neater, but we notice that the number of edges is the same, but the number of vertices is increasing. So at the start, if there were, let's say, 5 vertices and 8 edges, and next step there'll be 6 and 8, and there'll be 7 and 8, there'll be 8 and 8, and there'll be 9 and 8. Boom, we have reached n and n minus 1. This is a tree. Okay, this is a tree guaranteed only if this original thing was connected. If it's not connected, then the
Like
basic
this is the
idea
whole
is
concept of spanning trees. You delete cycles, you get trees. You delete cycles, you get trees.
not exactly, because see, usually what you do is you delete a random edge of a cycle and then you induct down. Here, I am not actually reducing the number of edges. In fact, I'm
Like
adding a new vertex.
you're just like deleting a cycle and making a tree out of it in some way.
Yes, but the problem is you're creating other trees, which we, as shown, are not too many, but it's still a bit unclear. So the formal way and the right way, as Siddharth said, is that the ratio of number of vertices to the number of edges is strictly increasing, because vertices are going up and edges is just staying equal. And essentially at some point you will have to reach a tree. Oh, and the other thing is, okay, let's say at the start the graph was connected. Then after we do a step, the graph should still be connected. Is that logical?
Yes, this is the main thing that if we just keep decreasing the number, keep increasing the number of edges, there is an upper bound on it, and it will stop there. It can't
Yeah.
go anywhere from there.
Yeah,
That's
because
the
we're
thing.
trying to keep it connected, but at the same time, we want to keep making the vertices increase. You have too many
Yes,
conditions. You can't go on forever. That's it.
yes, this is a rigid condition.
Yeah, it's that's sort of the thing with a lot of times you will see in trees. They're so rigid that like you want lots of conditions to hold simultaneously, and it's just not going to work out for everyone. Okay, so this was a cool problem. By the way, what happens if the graph is not connected? I leave you to think about that. It's not very hard. It's just slightly different. Um,
Like you are just making a connected graph out of cycle. In each move, you just make a connected graph. You can't delete the connectedness. So in some
no,
way,
but
you are
what if the thing was not connected at the start? Like, let's say
like say,
two
okay, okay. So let's
there were
say,
two connected
okay,
components.
yes,
Hmm.
okay. We have two different connected components. One component can go to a tree, another can go to a tree. Now, since
Correct.
these two are like uh not
They're basically
connected,
independent of each other.
yes,
Like
they
it's
are
basically
independent.
solving the problem for those individual trees, individual graphs.
Yes, yes.
Exactly. That's the idea. So that's actually another very common idea in graphs where sometimes they'll just give you that the graph is connected, but if they don't, a very simple idea is assume that it's connected. And then if it wasn't connected, you try to solve it individually for each connected component. Okay. We do not have too much time, but I want to do a very, very, very nice problem, which is one of my all-time favorites. And the best part about this problem is that, or okay, maybe I will not do that problem. Maybe we'll do it tomorrow. I don't want to do it at 10:30 in the night when everyone is bored and sleepy. Let's do this problem because also I promised that we might do a grid problem. Again, we'll think about it for uh 3-4 minutes because it's also getting late. After which we'll get into the discussion. Oh, and should I no leave it? You people can figure out what this problem is. Oh, also it's probably worth mentioning that these are cyclic. So like a of 2k plus 1 means a1 and a
So
0
like the indices are
a
modulo
minus
sum.
1. Yeah, exactly. It's mod 2k. A minus 1 is same as a or rather a0 is same as a 2k. Do I need the last condition? Probably. Okay. So, although I don't think the time I gave is up, like last 2 times also, but just to start off somewhere, let's read the problem. I've not read the problem. Suppose two endpoints of a n by n grid are marked. Prove that there exists a k greater than 1 and two k distinct marked points such that for all I, a2i minus 1 and a2i are in the same row, and a2i and a2i plus 1 are in the same column. So I can make a grid. 1, 2, 3, 4, 5. 1, 2, 3.
Don't
Five.
make 5, bro. It is like, okay, it's your
It's too
wish.
big.
No,
No,
it's
it's
your
fine.
wish.
I'll make 10 random guys. How many are these? 3, 5, 6, 7, 8, 9. Okay, you're right, it's too much. But still, it's fine. So I want some sort of kind of like a cycle here, right? Let's see. Can we find? Okay, this is a cycle. So basically what I'm trying to look for is like I'm going to label these as A1, A2, A3, A4. And I know that A1, A2 are in the same row. A2, okay, no, sorry, my bad. A2, A3 are in the same column. A3, A4 are in the same row. A4, A1 are in. Whatever. I'm not sure if I have exactly followed their conditions or it should have been A2, A3, A4, A1. But that's kind of the idea, right? You want a cycle. Is there any other cycle over here? It's a question.
It's the uppermost, the tetronymo, the uppermost. Like the uppermost square, then the
1 second, 1 second. I'll use a
okay,
different
okay,
color.
okay.
Yeah. Upper,
Then the lower, and then
okay.
2A1,
And then,
then 2A1.
oh, no, what?
Yes.
Then where?
Then it is like take that point to be A2I, the midpoint, A2N, A2K, and the upper one to be
1
like
second.
A2K minus 1. Okay.
Wait. So we started at A1, then A2, and you're saying say A3, then,
Then label A2 as A4.
okay.
The second one A2. Okay. A3
Then
as
this is
A5.
5, A6, then.
Okay. Okay. You're done.
Now I can't come back to A3. That's not allowed. Distinct mark points.
Okay.
That's not good. I think this is the only one.
But it is not given to prove that it is a cycle. You can just do it without a cycle.
What?
Like, is it mandatory to complete a cycle? I guess it
Yeah,
isn't.
yeah, you need
How?
a cycle. Otherwise, it's
Why?
very easy, right? There'll obviously be a path.
Yes.
Actually, even that's not very obvious, but no, that's much more doable. Like then I don't even need this 2k and all. I can just say k equal 2 or something.
But
I don't
like
know.
in cycle, just remove that A6, A1, A2. You have a path, you're done. You just remove the cycles and do the connectedness thing and get like that tree.
No, but
And
I
you
know
just,
2 endpoints are there in the n by n.
yes, yes.
So
So
you're
like,
deleting some stuff.
yes, yes.
And then
And then we will like have a cycle. We need
no.
a cycle.
If I delete A3, A4, A5, A6, there's no more cycle I can see at least.
Delete A2, A3. Like,
Delete A2, A3.
like make any path. Make any path that is possible. I'm saying make any
Fine,
random path.
something like this.
Yes, yes. You know that it is connected.
Sure. No, wait,
Connect.
why is the graph connected? It's not connected.
It is.
No. So how
Yes.
will you reach? How will I? These two are connected, but neither of these is connected to.
Oh, I'm talking about A1, A2, A3, A6,
Okay,
A5,
okay,
A4.
okay, okay. Sure,
Yes.
they are connected then.
You forgot to connect A3, A4. They are in the same row. Like I'm saying to connect
Fine.
everything that is in a row or column.
Okay.
Yes.
Fine, got it. So
Okay.
these two are connected. Then
Yes. Now delete like A2, A3 and A1, A2
delete A2, A3. Fine,
and A1,
delete
A2.
it. A1, A2.
You need to do it now until you get a cycle.
But how do you know I will get a cycle for sure?
Okay. You need to prove it.
Yeah, that's kind of the problem. Okay. So I spoke earlier about that interesting graph theory approach of these grids. And this is supposed to be kind of the most direct, not most direct, but whatever. So I again do the same thing, 1, 2, 3, 4, 5, or till n in general for an n by n. And I join them by an edge if I have, filled that particular. So like here I filled 1, 1, I filled 2, 1, I filled 2, 2, I filled whatever. I'm not even figuring out. Okay. What I know is that there are 10 edges, correct? And what has the condition become equivalent to?
False marriage.
No, wrong.
There is a cycle, so it's not a tree.
Okay.
Yes. Like we have to prove that there is a cycle. Because like if you get a cycle here, which is like 1, 1, 1, 2, 2, 5, 5, 1, and that's essentially meaning that 1, 1, 1, 2 were in the same row, then 2, 2, 1, 2, 3 were in the same column. And then you're basically doing a cycle in some sense on this graph, right? And
Yes.
why is there a cycle in this graph?
If it isn't,
Okay,
Okay.
how many edges, how many vertices are there in this graph?
there are like 2n vertices, and there will be like greater
And how
than
many?
some. Like if there are greater than n minus 2n minus 1 edges, then we are done. There exists one cycle.
But there are two endpoints, and each edge is what? It's basically a point because
Yes.
we joined 1 and 1 if 1 comma
Yes.
1 is a point.
Yes.
So there are
Just
two
prove
n
that.
vertices
Yes. Okay.
and two
Just
n
prove
edges.
that there are 2n greater than 2n minus 1 edges, and you will be done.
Yes, exactly.
And
So
yes.
if this was only a tree, that is there was no cycle, then it could have had only 2n minus 1 edges. But then it has 2n edges, that's a fact.
Yes. So it has a
So it
cycle.
must have a cycle. So
I
that's it.
saw a tree with a cycle. Do you want the photo of that tree?
Oh, I know what you're going to. Thank you. Okay, chalo. I think it's time also. Anyone has any okay, maybe I'll stop recording. Wait, the recording is on, right?
Only
Yes.
Pranav can stop it, I guess, or you can.
Yes. No, I am the host.
Okay.